Hi everyone, welcome to another round of IRIS-HEP Fellowship Talks. Today we have Braden, Mihir, and Rohith. Braden was mentored by Michelle and a few other people. Michelle, do you want to say a few words to introduce Braden's work?
Sure. Yeah. Thank you. It is my pleasure to introduce Braden Kronheim, who worked on this project, jet correction and simulation with Quantile neural networks this past summer with me, Harrison Prosper, and Raghu. Harrison's at Florida State University, and Raghu and I are from Davidson College, and Braden is a graduate student at University of Maryland. I think that this was a really fascinating project to work on, and there should be a paper up on the archive soon that we can point you to, and it's available. And it's a really, as you'll see, a nice, simple method that produces really fantastic results. So with that, I'll let Braden tell you all about it.
Hello, as Michelle said, I'm Braden Kronheim, and over the summer I worked on a project of doing jet correction simulation with quantile neural networks. So, okay, as a kind of summary of some of the terms I'm going to be using through this project, just so everyone's on the same page, I'm going to step through the jet simulation and correction process, which is currently used at CMS. And other detectors. So first, you use something like Pythia to essentially just simulate a collision at the Large Hadron Collider. And as a result of that, you just get a bunch of particles, leptons, quarks, gluons, and so on. Then the quarks and the gluons themselves are what we'll call the parton jets. So just the parton that causes a jet, which the jets themselves form through the hadronization and clustering phase, where one quark or one gluon essentially creates a whole bunch of other ones, and you end up with this mess of hadrons, which then we run a clustering algorithm on them, such as the anti-KT algorithm, and we end up with what we call the gen jets. These then enter the detector and they either actually enter the detector or they're simulated entering the detector using JONT4. Then some sort of algorithm like the puppy algorithm or charge hadron subtraction is used to remove particles from other events. And then a clustering algorithm is then run again, such as anti-KT algorithm, and we end up with what I'm going to call the raw RICO jets. Finally, then there's default jet corrections, which are applied generally based on like the transverse momentum and the eta coordinate of the actual forward momentum of the jets. And these are called the RICO jets, and these are what are typically used in analyses. So the kind of two tasks that I'm worked on over the summer using the quantile nets to do are what I'm going to call the jet correction task. So this is essentially just replacing these jet corrections with results from a quantile neural network, going from raw RICO jets to as close as we can to the gen jets. And then also a jet simulation where we go from gen jets to the RICO jets, bypassing the extremely time-consuming JONT4 simulation. The data set that we used was from CMS data and the DOIs there. So in order to like properly do either of these tasks, we need some sort of method of predicting distributions. Because for the simulation phase, you can have a single gen jet transverse momentum, which then, depending on exactly how the jet is reconstructed, how it interacts with the detector, you can get a range of possible RICO jet transverse momentum that all correspond to this, that all can be created by this single gen jet PT. So in order to properly simulate this process, we need some method of predicting distributions. And the same can be said for the jet correction, because a single observed jet transverse momentum could have been caused by a range of different gen jet transverse momentums. So we need some method of predicting essentially conditional distributions. Now, there are kind of two main ways of predicting distributions that have been used recently in high energy physics. One is a conditional GAN, and I mean, both of these methods are used elsewhere as well. the conditional GAN does essentially exactly what we're looking to do. It goes from a single input to a distribution of outputs. And conditional GANs work very well, and GANs in general. And you can see all these different papers, and these are just a small subset of them. However, the slight downside with conditional GANs and GANs in general are that they're very complicated to train, and they can be very finicky. So while they work, it just can be sometimes a bit of a pain to get them to work. And then the other method is normalizing flows, where we essentially map from one distribution to another distribution using a bijection. There's also ways of making these work as conditional normalizing flows. And frankly, these methods could also work for this particular approach. And they've been used in a lot of different areas. However, this is still a somewhat more complicated way of doing it. And the quantile nets, which I'm going to talk about, are actually, frankly, very simple idea. So to kind of compare them to some of the just more typical neural networks, the only real difference is in the loss function. So for normal neural networks, you'll typically use the mean absolute error or a mean squared error, which will, when you have a distribution of possible results, the mean absolute error will learn the median, and the mean squared error will learn the mean. Whereas the quantile loss function, which is, you can see down here in the mathematical details, depending on the quantile tau that you input to it, it will actually learn the corresponding quantile from the target distribution. And if you include the quantile as an input to a neural network, and then you change the loss function based off of that, you can actually create a neural network which learns this entire quantile function. So it'll, and that contains all the information that we need to map out the full probability distribution, while being a, frankly, very simple loss function. So in addition to that base loss function, we also have a regularization term to prevent quantile crossing. So when the quantile net is learning essentially all the quantiles, it should be learning some function that looks like this. This is a quantile function for a normal distribution with mean 0 standard deviation 1. And as you can see, it's monotonically increasing. Well, it's strictly increasing. And it is unphysical or mathematically not meaningful for this to have a negative slope at any point in time. So we introduce a regularization term, which is the slope squared if the slope is less than 0 and it's 0 otherwise. This has the benefit of only penalizing unphysical quantile functions, and it has a continuous slope, right? Slope of 0 here. So it's very helpful. And this was largely able to remove any unphysical quantile functions. So the other potential issue with quantile networks is that the quantile in and of itself is only a one-dimensional statistic. It doesn't mean anything to take the 0.5 quantile of a two-dimensional distribution. However, there's a way of decomposing a three-dimensional or n-dimensional distribution into a sequence of single-dimensional distributions. So here we have the conditional distribution of A, B, and C given D. And we can just take the probability of A given D, probability of B given A and D, probability of C given A, B, and D, three single-dimensional distributions. We multiply them together and we get the full distribution out. So this is essentially how we tackle the higher dimensional problems. Okay, so then how this actually works when we put into a network is we take an input jet, so PT, eta, phi, and mass. We do a one-hot encoding of whether we're going to predict PT, eta, phi, or mass of the target jet. And we'll include any previously sampled PT, eta, and phi, as well as a uniformly sampled quantile. These values are all constructed, well, the inputs and the targets are all constructed by just taking a standard input jet and output jet data set and kind of decomposing and turning each one of those examples into four as determined by this here. And the nice thing about this is that once you have this decomposition, you can just use a normal neural network architecture. So you can have however many dense layers you want, however many perceptrons per layer, whatever activation function you want. And then you just output a single value, and the loss function is determined by this quantile that you put in here. So the only somewhat weird thing is you have to be able to pass this information directly to the loss function, but it's not too bad. And then once you have trained this using standard gradient descent methods, when you go and do inference, the only difference is that instead of always having fixed inputs here based on the training data set, you have a fixed input jet here. And then you do a one-hot encoding to say you want to predict transverse momentum first. And you pick a random quantile, you run it, you run the network, and you get a transverse momentum out. Then you put that back here as one of the previously sampled values, change the one-hot encoding to predict eta, and run it again, and so on and so forth. And after 4 runs, you will have a sample of PT, eta, phi, and mass of the output jet given this input jet. Yeah. So these actual predictions, like, it's an interesting question to ask, like how we actually use them. So for a one-dimensional problem, the kind of rawest output is just this quantile function. So we, instead of randomly sampling the quantiles, we just go between 0 and 1 in a discrete manner, and we map out this function. We can then invert that function to get the cumulative distribution function, and we take the derivative of the quantile with respect to like the transverse momentum, and we get the probability distribution function. However, instead of going through this whole process, we can also just uniformly sample the quantile, uniformly sample a quantile, get the value from the quantile function, and then you end up seeing that it'll actually follow the values that you sample. You'll sample them with the probabilities according to this distribution here. So you can just directly sample from this distribution, which is fine in one dimension. It's pretty much the only way to effectively use this in higher dimensions, though, because you would have to map out an n-dimensional probability distribution, which would be very time consuming. So this is this is just uniform sampling of the quantile is the most effective way to make samples from these. And then once we've made the samples, we need to be able to determine if the distributions that they predict are actually reasonable. So what we do is we take the predicted distribution for a fixed input, and then we take the target value from the test set that corresponds to that input, and we determine the quantile of this test set value according to the predicted distribution. And then we collect all of those quantiles across the training set, and we just plot the distribution of the quantiles. And assuming that the distributions predicted are actually meaningful, this should be essentially a uniform distribution. Yes, so here's some of the results for the jet correction problem. So this is just for transverse momentum. The results are very similar for eta, phi, and mass. What we see here is that the marginal distribution is pretty much perfect. And when you look at the ratio of the counts in each of the bins, you can see that while it's maybe not quite as perfect as it looks like in this graph, it is still very, very good. And the reason why we have these little error bars is because for all the test set values, I took one sample from the quantile net 1,000 times, and I created a histogram for each of those. And these error bars just kind of represent the uncertainty and the number of counts in the bin across all of those histograms. And then over here, we have the distribution of quantiles. And you can see that it's not quite perfectly uniform, but it is very, very close. And the noise seems to be pretty random. So this indicates that the distribution it's learned are actually generally meaningful across, at least on average, across the data set. And here are the results for simulation. And we see essentially the same thing. The marginal distribution is just a smidge off right at the lowest values, largely just because there's a hard cutoff in the transverse momentum values we use. So, yep, those are those results. And thank you for your time. Does anyone have any questions?
Any questions for Braden? Okay, thank you, Braden.
Thank you.
Up next, we have Mihir. Mihir was mentored by Mark and Matthew. Do either of you want to say something about Mihir's work?
Sure. Yeah, I'll just mention that. I mean, I think Mihir is going to say this as well, but Mihir is a university student at the University of Illinois at Urbana-Champaign, where both Mark and I are at. And he, I thought, did a really nice job with a very ambitious project, and on applying deep learning methods for the matrix element method. But I'll just turn it over to him because he's going to tell you all about that.
All right, so I'll just get started. Let me turn my video on. So hello, everyone. My name is Mihir, and I will be talking about my project with the IRIS-HEP fellowship that I did over the summer that involved using deep learning for the matrix element method. I was mentored by Matthew and Mark, and I'll probably thank them in the upcoming slides towards the very end. So just before we begin, I really wanted to set the tone as to why this project is important. The LHC's future is probably going to have a dramatic increase in luminosity more than energy, which means that we're probably going to get a large amount of collision data, which has a lot of complex events in the future. And what we want to do is make full use of this data by incorporating and correlating as much of the available information within each event as possible. Now, right now, there's a few ways to do this. The one that is the most widely used in this context is just regular machine learning models like neural networks and boosted decision trees. They are black box methods, though, and they have their own advantages and disadvantages. An alternative to those is the matrix element method. So the matrix element method, as is shown here, is the ab initio calculation of an approximate probability density function for an event which has a observed final state particle momenta x with a process xi with the theory parameters of alpha. And this is what the actual calculation of the probability density function looks like. As you can see, it's a high dimensional integral, which is difficult to compute because it's very peaky. But one thing that I want to highlight in this entire equation is actually the matrix element squared part, because the matrix element is going to actually incorporate the dynamics from QFT because it has a human understandable meaning in terms of transition probabilities from one state to another. And this probability distribution that we get can actually be used in a number of ways to search for different phenomena at particle colliders. So for example, you could do sample likelihood with it, where you try to estimate alpha measurements with maximum likelihood, or you could create a Neiman-Pearson discriminant for different kinds of process searches or just hypothesis testing. But for the purpose of this talk, all we need to care about is the fact that this probability distribution is a function that can be numerically calculated and has this inherent physics-driven information that can be useful for future measurements. Now, the reason that MEM has many advantages over ML is one of them is that it doesn't require training. So if you had a smaller sample size, the MEM calculations would pretty much be invariant to that. It also incorporates all available kinematic information, including correlations, and it has a clear physical meaning in terms of transition probabilities in the quantum field theory. However, obviously, it also has its own drawbacks. The major limitation is the fact that it's very computationally intensive. So if you want to calculate this probability distribution for an event like this TT bar Higgs production, which has so many different final particle states, the calculations would probably take minutes per event. And for context, if you want to sample like 1 million events, this is going to take a massive chunk of time. So in order to make this entire research process that involves MEM a lot more sustainable, one of my mentors, Dr. Mark Neubauer, actually proposed that we use machine learning methods to approximate these calculations instead, so we have a sustainable method to actually perform these calculations. So this is what the current pipeline for the calculations looks like. This has been dockerized and containerized by my other mentor, Matthew, under the context of the ScaleFilm project. Each of these containers are parallelized and can be run on the supercomputer that we have access to at the UIUC. Each of these containers, again, have their own particular tasks, and I won't really go into the details, but you can see that this one will do particle level simulations and particle interaction simulations. You have detector level simulations, some basic event selection, and finally, the final container, which actually performs the full matrix element method calculations using momenta. We can also see that the entire pipeline actually takes 45 minutes for 200 workers for 300,000 events of this particular process, which is the dilepton final state Drell-Yan process. So it is important to note, however, that this is probably the easiest process that you can simulate. Most other processes for any real analysis that we talked about earlier will probably take minutes per event. So these numbers would look way, way worse. And we can also see that the final container for the MEM calculations actually takes the majority of the time in the entire pipeline. Of course, if it wasn't possible to parallelize this, then the serial time that it would take would be 150 hours for the entire pipeline and 113 hours for the final container. So we can clearly see that this is a very computationally intensive process. So this is where the objective behind deep MEM really becomes apparent. We really want to address the challenges of MEM while retaining the benefits. We want to keep the transparency of these MEM calculations while reducing the time that is actually required to produce them. And one way that was proposed to do this was to just use deep neural networks. We know that DNNs are very good at arbitrary function approximations, and they scale really well with data. So if you give them more data, they're probably going to give you better approximations of the nonlinear function that they're trying to approximate. And the idea is, okay, we can just replace the momenta calculations from the pipeline that I showed earlier with a neural network that has been trained on these momenta outputs. Of course, it is important to note that most final calculations, so for like final papers or final abstracts, will probably be performed using the entire pipeline because you want the stability and accuracy of the pipeline. But during research, if you want to make small tweaks to stuff like event selection, usually what happens is you have to run the entire MEM calculation pipeline all over again, which is, again, 150 hours of serial time all over again. However, when you're using deep MEM, as long as you have the same final state, you can reuse the neural network for approximations. And this is where the sustainable part of deep MEM comes in. So once we actually introduce deep MEM into the mix, this is what the pipeline would look like. We can see that deep MEM is actually trained using momenta weights that we got from the original pipeline. And instead of passing the root T trees through the final container, we can actually give them as inputs to the deep MEM module. And instead of getting momenta weights, we get log transformed approximate values for these weights. Now, for the exact same process that we talked about earlier and 300,000 events, the inference time for this module will be around 2 minutes, which is a decrease over the 34 minutes of parallel time and 113 hours of serial time that we saw before. Of course, it is important to mention that there is a certain amount of training time involved, but it only really needs to be done once for a particular final state, and that takes around 18 minutes. So now we can actually talk about the data that was used for this project. For this particular project, we only considered the simple Drell-Yan process, which has the lepton pair final state that looks something like this. So we have the root T trees that are produced by the first 3 components of the pipeline that I showed earlier. And after some basic event selection, we can actually use the flow momentum of the final state particles that we care about. So in this case, it will be the 2 leptons that are produced, as well as the 2 significant jets that are produced, as well as the missing transverse energy. Now, it's important to note that there's no explicit MET in this particular scenario, but if this same module is used on other analysis that has weakly interacting particles, for example, then there will be some MET. And because of this, we decided for generalization and completeness purposes that we would use MET for this analysis as well. We also know the fact that particle mass is actually a very good discriminant. So we actually keep the neural network blind to it. We don't really want the network to just look at one particular parameter and then completely base its predictions on it. So in order for generalization, we actually exclude that parameter. So this is what the inputs finally look like. You have the transverse momentum, you have the eta or the pseudo rapidity, you have the phi components of both the leptons and the 2 significant produced jets, and you also use the magnitude and phi of the MET. This gives us a total of 14 input parameters for this process. And the outputs are simply the negative log transform momenta weight values that we got from the pipeline originally. It is important to note that this entire data selection process was heavily influenced by this paper, Breaking the CPU Barrier, which I've cited here. There was a lot of influence from this paper in order to actually choose which kind of data we want to, which particles we want to look at. And finally, the data set that we use has around 300,000 events total. So the first part of my project actually was spent on creating something called a multi-processing data loader. Now, the data set that we have right now is only 300,000 events, and it completely fits in memory. But If the same analysis is done with other processes with more sample size, maybe like 1 million or 1 billion events, we will run into a problem where the data set doesn't fit in memory anymore. And the issue is that this PyTorch inbuilt data loader actually is mostly geared towards image data and computer vision data. So the way it works is it loads individual samples, collates them all together, and then passes it to the neural network. Obviously, if you have contiguous and tabular data, then this is not very efficient. And there's no real out-of-the-box solution that can actually address this issue either. For example, the fact that tabular data is loaded faster in chunks is something that is addressed by PyTorch Lightning. But if the data set is too large to fit in memory, then the user has to deal with that issue themselves. So the module that I created, the data managing and loading module, actually is pretty versatile, and it can be used with any analysis that involves both root files, so mostly high energy physics analysis, and also machine learning in PyTorch. The way it works is you parse these root T trees that you have based on user input. So whichever particle the user actually cares about. And then you use the inbuilt multiprocessing library that Python has to create a C-based construct that we can call the cache of data. The good thing about this cache is that you can actually share this data structure with other processes that you spawn. So all that's left is to actually spawn these processes using the inbuilt PyTorch data loader and then load data from this cache that we have. And once you've exhausted the cache, all you have to do is replace this with a new segment of data set from your memory. So doing this, we actually get significantly much faster results in comparison to the inbuilt data loader. These numbers that I have here are for 100 epochs of the Momenta test data set. And we can see that we get 1/10 of the time pretty much of in comparison to the inbuilt implementation. So talking about the actual network architecture that we trained on, this is what it looks like. To start off with, we used a very basic, fully connected deep neural network with 5 deep layers of 200 nodes each. We also split the training data. We also split the entire data set into 80%, 10%, 10% bins for training, testing, and validation purposes. And so at the end, what you would have is around 240,000 training samples and around 30,000 validation samples. And you use this to train the network for 100 epochs, and we can see what are the results we get. So once again, this is the plot for the results that we got. And this is for unseen data, so data that the neural network hasn't trained on. And this is a histogram plot that basically plots the counts in terms of arbitrary bin values for the weights that we predict. And we can see that we get a decent visual fit. We can also quantify this by using mean absolute percentage error as a metric, which is basically the absolute average percentage deviation of your predicted value from the actual value. And we get a value of 1.6%, which tells us that we're on the right track. However, we do see a major error here, or a major issue, that the network cannot really generalize on these bins at the very beginning, because we have these outlier ratio values. And the reason that we think this is happening is because of the fact that we have a smaller data set relatively, because we only have 300,000 samples, and we don't have as many events in these bins, so the neural network is not able to generalize within the phase space. So one way to fix that would be very simple, just scale up the amount of data that you have. But as I explained in the pipeline before, that is not a very trivial task. So the approach that we chose instead is to look at more generalized architectures, maybe more novel, complicated architectures that could solve this problem. And that is exactly what we did. So we looked at the architecture known as residual networks. These are architectures that incorporate skip connections in the neural network. So these basically ease training by providing these shortcuts, or you can think of them as short circuits, for the gradients to actually pass through and update all of the layers that are present in the network. And we've also seen that these ResNets actually have very good empirical results on very aggressive deep networks. So for example, the image recognition competition in 2015 was where this was actually invented, and it pretty much blew every single other architecture out of the water. And the hypothesis as to why these work is because they actually address something known as the gradient vanishing phenomenon. So when you have smaller gradient values, when they are sent back during backpropagation, they don't end up updating all of the earlier layers of the neural network if it's super deep. However, with these skip connections, you can actually transmit these values successfully and update all of the layers, giving you better generalization and better performance. So the two architectures that we look at are ResNet A and ResNet B. ResNet A is 5 deep layers followed by a skip connection. ResNet B is 6 deep layers followed by a skip connection. And the reason that we need to take a look at both of these is because we want to ensure that the improvement in accuracy or performance that we get is because of the skip connection and not just because we improve the complexity of the network. So ResNet A, for example, is less complex than the original DNN. ResNet B is more complex. So ideally, we want to see good results for both of them. So these are the results that we get by using ResNet A. We actually see much better generalization. You don't really see the outliers anymore, even though we do have large error bars over the bins that don't have as many samples. We do see a decrease in the mean absolute percentage error, which is only around 1.4% now. And we see a very good visual fit. So we can actually argue now that adding the skip connection was what improved the results because this network is less complex than the one that we used before. And of course, with ResNet B, we see even better generalization, lower error bars and better ratios, and lower mean absolute percentage error. However, this was kind of expected because we expected that a more complex network with a skip connection would give us even better results because we're leveraging the depth as well as this new novel architecture of skip connections. So to summarize what we've done in this project, we implemented machine learning methods to approximate these matrix element method calculations and demonstrated that this approach is actually viable, at least on the simple Drell-Yan process that we showed. And we implemented a versatile multiprocessing data loader to efficiently load data from root files. So the versatility part comes from the fact that anyone who has root files as well as machine learning in their projects can actually use this data loader. And finally, we implemented residual networks for better generalization and better performance, as we showed earlier. The next step in this effort would be to actually go beyond the simple Drell-Yan process that we showed to other processes that have more complex decays and more final state particles. So we want to ensure that this methodology actually generalizes to other processes that are more complicated. And of course, DeepMEM is actually an open source Python library that is distributed on PyPI. And if you have similar data sets, can be used on that. And it's easy enough to install it. You can just do pip install DeepMem through your shell. Finally, I would like to acknowledge both my mentors, Dr. Matthew Fikert and Dr. Mark Neubauer, because their help was absolutely incredible throughout the project. They helped me formulate the problem, understand it, and create an actionable solution that could tackle this problem and solve it. And of course, a big thank you to IRIS-HEP and NSF for actually funding this fellowship. And with that, I would like to pass it on to the audience to see if they have any questions. Thank you. Yeah.
Nice job, Mihir. There is one question from the comments that I'd like to read first before I get to Alex's question. So Harrison Prosper had to leave. So anyway, here's his question. Unfortunately, I have to leave. This is very nice work by Mihir, but here's a slightly cheeky question to Mihir. Why is MEM less of a black box than ML, given that both use exactly the same matrix elements squared, and the discriminant that you have written down is identical between ML and MEM? Moreover, go ahead. I'll let you answer it first, and I'll do a second part. And then moreover, the ML can, in principle, be parameterized in exactly the same way as in MEM. Therefore, in the end, both can be made mathematically identical. Any thoughts?
Yeah, so from what I understand from the question, I'll try to repeat it, is why is the procedure that we're doing less of a black box than actually just using ML from the first place, right? So from that, the argument that I would say is the fact that, okay, we are using ML in order to approximate these deep MEM calculations. However, when you're doing just ML at the very beginning, like I showed over here, you have an input, a black box, and then an output for any kind of analysis. However, here, we actually know what MEM is actually trying to tell us. We actually know what it means. And the only thing we're doing is approximating the calculations. So I would argue that the black box here is still a lot more transparent than just doing ML for any kind of calculations.
Yeah, can I make a quick comment? Yeah, I think Harrison's not here, I know, but I think when we said that the matrix element method is less of a black box than the ML method, it's exactly what Mihir said. We were referring to the more traditional using some deep neural network on the event kinematics to make, energies, angles, masses, and then train a discriminant. What I think when we talk about the machine learning approximation of the MEM, I think that's what Harrison is referring to, and is maybe that in that case, it's just an approximation. There is also no information in there that's physics driven. But yeah, the matrix element clearly has, the dynamics of the standard model in it, and it's completely interpretable, whereas there are challenges in interpreting a model of just sort of like a fully connected deep neural network for event classification. So it is exactly what Mihir said. Yeah, I think Harrison might have been a little confused about which ML we meant. And yeah, once you can approximate with ML, it essentially reproduces the mem, but there's still no physics information in that. Anyway.
Well, thank you both for clarifying that. I hope Harrison can watch and see the answer later. So I have a question from Alex. Alex.
Hey, thanks a lot for this talk. This is very interesting work. I'm wondering about the performance that you're quantifying, like for example, on slide 14, the average mean absolute error that you're quoting there. To do this comparison, you need to compare to some ground truth, for which I'm assuming you're taking the weight that you get from momenta as ground truth, right? For comparison. Do you know how large the uncertainty is in momenta from the integration? It's only 3 particle final states, so it might be extremely accurate, but I'm essentially wondering how large that uncertainty compares, like how large the uncertainty compares to the value that you're quoting here, whether effectively you are hitting already the maximum possible performance, because now there's just like so much noise that you can't do any better.
So I don't actually know the actual value of the maximum intense uncertainty. Oh, sorry, the uncertainty that comes from momenta. But as you said, it's only a 2 particle state, so it shouldn't be that high. Another good point about like the mean absolute percentage error is that this is only a metric that tries to quantify this instead of saying that it's a visual fit. There are other issues that come with MAPE, the fact that you can't actually divide by 0, for example, that we have effectively avoided because log 10 is going to like ensure that there's no 0 values. So in general, I would say that MAPE is only there as a metric to tell you what this is doing, and not as a uncertainty quantification metric. But I think this question about the actual uncertainty of momenta is probably more directed towards Matthew, because he probably knows the actual value.
Yeah, that's a very good question, Alex. Off the top of my head, I don't remember what those were. And I'll actually just mention that like Mihir did a great job with this project, actually, like in spite of me, because I spent most of the time trying to wrangle momenta to actually work in parallel in a manner that wouldn't kind of crash. So I'm still I can look up those values just because for my own benefit they would be good to refresh myself on, but I don't have them offhand.
Yeah, Alex, excellent question. You're right on. Usually these numeric integrations, they're sort of sub %, but they're not 0 and they're not. So you're right, this might not be that far from the actual Vegas integration error. And you can dump that out. So that's a good suggestion, and you're right on.
Okay, thanks.
Okay, Gordon, you have your hand raised.
Yeah, so fantastic talk and some really interesting work. Actually, my question was I had two things I wanted to know, but the first one is right along the lines what Alex was asking. Given you see, especially with that 7-layer network, you're down at what was it 1.2 or something, the average error, and that the histogram you had there of the errors as a function of the weight looked fantastic. Why would you go back to the slow method for the final calculation? Were there any experiments done to see if it made an actual noticeable difference within errors?
So the way I guess you would do it is to actually use the values that you get from momenta and do some kind of analysis, like as we said before, like using maybe a Neyman-Pearson discriminant or doing some maximum likelihood stuff and comparing the approaches with momenta that we have through the actual pipeline and this approach that we have, and then seeing if we actually get any major difference. But the major issue here is the fact that you said that why would you go back to the slower approach ever, right?
Yeah.
And the reason is because it has more accuracy and stability. So if you're actually performing final calculations for a publication, that 150 hours of serial time or 34 minutes of parallelized time is not as much. So if you want to publish, then it's probably better to go with like the safe method.
Yeah, I get it. But you said it has more accuracy and more stability. And I look at this plot and I say, this is not going to be the dominant error in the analysis in the end. And it's a heck of a lot faster. So why should I burn that extra, what was it, 113 hours or so of CPU when it's just not necessary?
Honestly, this is a bit of just a sociological thing. Knowing how
Okay,
Atlas reviews,
perfect.
how
Okay.
Atlas reviews go, I can imagine the arguments.
No.
Yeah,
That
you're using this
answers.
as yeah, I
Yeah.
can think pre-publication to be a requirement to just make a final
Yeah,
pass.
that-
But you're right,
that-
Gordon.
I'll
totally.
also just kind of jump in to say, like, as a compliment to like what Mark was saying, like while I'm very pleased with like the work that Mihir has done here, we should also maybe like again stress that we've shown this for Drellien, and that we have yet to actually like go and attack like much more complicated things and also more interesting things. Like we haven't even done this yet on like, you know, TT bar or something like that. So
Not even on TT bar. That has got to be one of the more complicated systems.
Yeah. Some of this comes about not really that seeing Austin Bays, who was an Illinois PhD student, struggle through TTH matrix element, and you know every little change you make, you have to rerun the whole calculation over, and we wanted to avoid that loop. Yeah, but you're right.
That's right. And this is what actually was my second question. Was I assume in the training it's holding not only the matrix element calculation but also the transfer functions, everything else like that, right?
In the actual momenta calculations, yeah. So if we go back to the
I mean that's what the deep the neural net is learning.
Right. So there must be like a latent representation of all of these components.
Yeah, which is totally no. That's totally okay. I just wanted to make sure I understood what the inputs versus the outputs were.
Yeah, so the inputs are just very straightforward. They're the four momentums of the particles that we are considering. So the leptons, the jets, and the met, which again, we said we don't really need met here. But
from the detector, from the detector, right?
Yes, the simulate, yeah.
Yep.
Yeah.
Okay. So
Matthew can actually probably corroborate that. But
no. It's okay. That this was actually making sure that my question made sense, which it still may not. But so the last time I did a matrix element analysis was back in D0 on a Higgs analysis, and it's nothing as complicated as I think, Mark, what your student had faced. But my memory is that the place we did most of the tweaking was adding new diagrams, messing with how we calculated the transfer functions, all those things. And wouldn't messing with any of those require rerunning the complete chain?
So the idea here, and again, I will probably defer this to my mentors later, but the idea here is that with the neural network, what you're trying to do is encode the final state. So for example, here we're encoding the part that, okay, this is a Drellien process, which has a dilepton pair at the end.
But so, you're encoding more than that. You're also encoding
can you go back to the equation
effects and.
Yeah, Gordon, you're absolutely right. I mean, if you look at anything that changes in the current, I mean, what this thing is doing is it's just taking the final state four momenta and it's learning this integral. And anything you change in the integrand, like if you have new PDFs or if you have new transfer functions, technically, you have to redo this. And maybe you're right, Gordon, in the end, maybe most of the tweaks are actually require that. That would be a bit unfortunate, but you might be right. But once you have that, then things like systematics, like what happens if I change, it's true that would be a transfer function thing.
That would be big. Yeah.
But I wonder if you could use to explore some systematic, effects and variations without having to redo the mapping. But you might be right. You might be right, Gordon. It's still an open question of exactly how useful this is. Yep. But yeah, technically, if you changed anything in the integrand, W or F's, you'd have to, or M, you'd have to redo the whole model training.
Yep. So
once you have it, we could explore different, differences. What happens when you go to this selection, this region of phase space? Well, in the past, you'd have to recalculate. Here, you could just use the function to extrapolate or interpolate, maybe. So that was our hope. But you're right.
I'll just finish by saying, Mark, that you had a workflow that you showed me here a little. That had all the various blocks and the containers. And once you've got that workflow, it's a crank you can turn, and the fact that you can just substitute one block for another, like the actual mem versus the deep mem, makes it very easy to just experiment with, like along the lines of what Mark said. So, having this and now being able to plug in and remove different parts, I think really allows for innovation. And Mark, I'm pretty limited in my thinking when it comes to matrix elements. So somebody smarter than I may come up with lots of uses for doing experiments around this as well.
Yeah.
So really,
thanks, Gordon.
really
Yeah,
nice work.
This pipeline, Matthew's pipeline of this is really enables. I mean, Matthew should comment. I guess it's there. It's like 30 minutes to basically turn from some physics inspiration via MadGraph to full probability densities and simulated events.
Yeah, I remember from D0, it'd be a week. It was over a week every time we made a mess.
I asked Matthew why someone didn't do this before, and he said, and I think we kind of concluded that no one was crazy enough to try to containerize all this because it was a lot of work. But now that we have it, Matthew, I don't know if you want to comment on its utility, but this was, this sets us up to do interesting studies for.
I think you should publish it. Frankly.
Yeah, I mean, I will. So we definitely want to follow up on Mihir's work, and Mihir, since he's a final year university student at the University of Illinois, we're happy to hear that he's going to stick around Mark's group and continue to work with us on this. But I would agree with you, Gordon. So these containers that we have in this pipeline, like these are all publicly available on Docker Hub under Scalefin, Scalefin's Docker Hub. Yeah, and I'll mention the fact that to maybe temper some excitement, we are using Delphi's here to do the detector simulation. This isn't like full Geant, but
it's a frickin' container which you can change the pipeline. But,
yeah, exactly. So like on NCSA Blue Waters at Illinois, like I can the way that I have this set up right now is you just give me a physics hypothesis that you can express in some form of MadGraph, and I can just basically slap that in and scale out as necessary. And then under an hour, we have the final, both the Delphs and the Delphs files, the event selection, and then the momentum weights.
Yeah, Matthew, this is like gold. I think this should be like a separate product's the wrong word for it, but it should be put out there, because I would think a lot of people could leverage this, and then being able to have tools like this deep mem, which you can sort of plug into the side. And I get it that it can't do everything yet, but this is how all projects start. I think there's some real potential here. There are a lot of people doing matrix element analyses, and having this ability, and maybe not all of them running at NCSA, but having that ability would probably attract a lot of people. A lot of people would get very interested in this.
Yeah. Well, I'm glad to hear that, and I can speak for Mark, Mihir, and me when I say that if people are interested in this, or if people have questions, that we definitely welcome interactions and questions. So we'd love to follow up with people more.
Yeah, thanks, Gordon. And we have been trying to socialize that we have some dark matter experiments. So if you're using this pipe, I mean, it's a generic pipeline Matthew put together. But thanks, Gordon. Yeah, it's feel free to get the word out. Hopefully, Snowmass might make some use of this. And
definitely.
Next up, we have Rohith. Rohith was mentored by Louis Guillaume. Louis Guillaume, do you want to say a few words about Rohith's work?
Hi, everybody. So Rohith he just finished his undergrad at Berkeley. I worked with us in the Atlas group for a while now. Previously did some work, I think, on the W plus D cross-section measurements. And he's now continued at the LBL theory division doing a theory project there. However, today we'll talk about the work he did with us this summer as part of IRIS-HEP on a kind of a new kind of method to do charge particle track reconstruction.
Okay. So today I'm going to be talking about the work I did this summer for IRIS-HEP with Professor Heather Gray and Dr. Louis-Guillaume Gagnon at UC Berkeley and LBL. So I explored the use of the approximate nearest neighbors technique, or ANNs, for particle tracking. And this work basically builds off of work done by Sabrina Amrouche in the paper listed on the slide. So in a nutshell, ANNs are hashing techniques which are used to find the approximate nearest neighbors of a point in n-dimensional space. And in our case, since we're dealing with the inner detector, 3-dimensional space. So ANNs basically work by creating a binary search tree of points. So our search time gets reduced from O of n to O log n search time. And the basic question is, can we use ANNs to find track hits of particles in the collision events at the LHC and in the future in the HLLHC? Since, I mean, luminosity is increasing by an order of the magnitude, current particle tracking algorithms can't really keep up with that. So we're trying to find novel particle tracking algorithms to just keep up with all the data. So here's a diagram that shows the steps of the ANN process. So the first step is creating an ANN index, which is a structure from where we can make queries from. So we first consider a space of n points, and the points in our physics-related case would be the hits from the particles within the tracking detector. So we basically do a recursive splitting of the space by constructing hyperplanes between two random points in the same section, and the points are assigned to either side of the hyperplane according to a metric. So in the end, you basically have this partition space where particles closer to each other should be considered in the same partition. So the leaves of this tree would be called buckets, and they're going to have a maximum of k points. So suppose we want to search for a point, we will search for buckets within all trees that we create. And we search these trees using a priority queue, and we eliminate all duplicate points in the bucket to create a sort of bucket union. And then we sort for the point that we want according to a metric, and then we would return the k nearest neighbors to point B. So that's in a nutshell how the algorithm works. And here's two images from the creator of the Annoy library. And on the left is a field of points that are being divided into several buckets. And on the right is basically bucket union centered around one point. So on the right, we basically have queried for the point in the center of that like red star thing. And it has given us the nearest neighbors according to this method. So to get familiar with the ANN algorithm, I basically decided to implement the ANN from scratch. And then I tested it against the Annoy library, which is a popular library, which is used in Spotify for song suggestions. And the major difference between my code and Annoy's code is that Annoy builds a binary tree only up to a memory limit. So it builds it up to 2 times of the memory taken by the vector of points that's given. And then it uses a forest of trees and a priority queue to get the k nearest neighbors. My scratch code builds binary trees up to hashes of k buckets, and it immediately partitions the space into points. So when we test both methods with 20,000 points generated with ACTS, after like optimization and all that, both my code and Annoy build the ANN index in about 100 milliseconds and take about 10 microseconds to execute a query. However, I found that Annoy's physics performance is superior to my code. So for the remainder of this talk, I'll be talking about Annoy. So here are a bunch of preliminary tests of our ANN physics performance. So we simulate an event with ACTS, with Pythia for particle generation and pileup, and Petrus for detector response. We use a TT bar sample, and we see that the PT is quite low. The PT cut's quite low, and we created a forest of 5 trees. We queried over all particles with bucket sizes of 20 and 50, well, maximum bucket sizes. And for a bucket size of 20, we found that the time to query a point is 500 milliseconds. And for k equals 50, it's about 1 second. And then we do a bunch of physics tests where we basically test how well it's able to pick out tracks without actually reconstructing tracks. So what we do is we scan a few definitions of the metric. So we have the Euclidean norm, which is the standard L2 norm, the Manhattan norm, the L1 norm, the cosine distance, which is it's like an angular distance, and a dot product distance, where it's basically a cosine distance scaled by the length to the origin. So here are some histograms that show the different performances for the choice of metric. And the quantity we observe is the frequency of occurrence of the most populous particle per bucket. And the further to the right the distribution shifts, the better the performance of the ANN, because we're able to properly account for the entire track. So the two major takeaway from these charts is that obviously when the bucket size is larger, the distribution moves to the left. And more importantly, it's clear that the angular or cosine difference is the most successful choice of metric for ANN. And we'll talk about that in a bit. So before that, I just want to show the difference in physics performance between Annoy and my Scratch code. And here's a slide where we have the same type of histogram that I showed before. And we have a bucket size of 100 hits, and we use the angular metric for both code templates. So we have the Annoy code on the left and my Scratch code on the right. And as we see, the mean max frequency for the Annoy code is about 3 times higher than it is for my Scratch code. But on the other hand, if we look at the entries in each histogram, we see that with Annoy, since buckets are not created immediately, we need about 10 times more queries than we do with my Scratch code, whereas we only need to query the amount of buckets that we've created with my Scratch code. So this excess amount of queries will lead to a significant bucket overlap, which will in turn lead to the creation of a lot of duplicate tracks by the Kalman filter. And we'll see how this throttles the ANN performance when we integrate it into ACTS. Okay, so again, to touch upon the choice of metric from before, we found that the angular metric is the best choice to determine particle trajectories, in part because for high PT particles with linear hits, the group of those hits would be 0 if we sorted them by the angular metric, and they would thus be likely classified in a bucket. And the other metrics would create buckets with clusters of particles, which could perhaps be useful for low PT tracks, but yeah. Ultimately, we would want neural networks to determine the best choice of metric throughout the detector, and that would ideally give us the best performance. So here's just a diagram with a hypothetical high PT track given at the top, and at the bottom is basically how different metrics would result in different nearest neighbors being picked out for the query point. So as we can see, the angular metric would pick out the track, whereas the other metrics would struggle a bit. So the next step we do is we integrate our ANN with the ACTS Kalman filter, and then we analyze our ANN performance as compared to the nominal, which is the case where we have one giant bucket with all of the event points past the Kalman filter. And this is what is currently done. And the ANN parameters we're going to use are K for bucket size and N for the number of queries. So assuming that we randomly query for our event hits to create buckets, as an initial benchmark, we run our Kalman filter with the ANN at several values of N and at several values of bucket size or the number of queries, and we basically plot the fraction of total points that were included in the Kalman filter. And empirically, we arrive at the formula N divided by 0.1K as the minimum number of queries we need to cover all hits in our event. As a second benchmark on the left, here's an event with arbitrary ANN parameters. So we have tracking efficiency plots of PT and ADA, which are binned measures of the percentage of truth particles with matched tracks. So for the PT plots, the first bin can tell us the quality of the algorithm. And in the nominal case, the efficiency in the first bin is 0.80. So with our ANN test, we'll aim for these numbers in that range. And the plot on the right shows how this changes as a function of the number of queries. And for example, how a bucket size of 100 is better than a bucket size of 50. So with our ADA plot, we can see that if there are any asymmetries, so in this case, we see a definite asymmetry, which means our random queries don't cover the entirety of the detector equally. But oftentimes these type of ADA plots are common for single events, and they eventually correct when we include many events. So in our initial speed test, we take one event and run it on 2 ANN configurations, which are given above in blue. And then we compare them to our nominal configuration, which is on the far right. So we see that there's a significant asymmetry in our ADA profiles, and that's just the result of running one event, so it's not really a problem. And while the PT plots look okay, we can basically notice that the time it takes to process both ANN configurations is about 5 times slower than the nominal. So I guess that's the first thing that we tackle, or we need to tackle. So the likely culprit that's slowing down our ANN is the amount of duplicate tracks being created, as I showed in that plot where in the slide when I compared my scratch code with the annoy code. And we can see about 5 times more duplicate tracks are created per event than in the nominal case. And this is, again, to the fact that when we query for points in the ANN, there's a lot of bucket overlap. And we basically want to find a way to diminish this overlap. Otherwise, the ANN performance will always be stymied by this sort of thing. So the first obvious way to mitigate overlap is we try to continue randomly sampling our hits, but we don't allow any duplicate hits per bucket. So with this configuration, we find a 70% decrease in runtime, but a 30% decrease in the first bin content in our PT efficiency. So since this gives us a speed up, we can perform a more complete analysis with this. So when we run our analysis with a bucket size of 100 through 100 events, and we notice how the ADA profiles are symmetric after we include several events. So that's good. And we vary the number of queries to observe the performance, since the empirical measure we talked about before is not necessarily applicable with the new query strategy we have right now. So for example, in these 2 cases, we see that while the difference in 1,200 queries isn't that much quality-wise, there is a significant drop in runtime. So also the duplicate rates have dropped, but they aren't at the levels of the nominal yet. So in this slide, we continue the previous slide and reduce the number of queries to 100, as well as show the nominal performance at the very bottom. So we see that in the unparallelized bucket case, to get a definitive speed up over the nominal, about a factor of 2, we have to take some track reconstruction quality losses. So steps forward would center on how to mitigate these losses. So the next clear step forward with guaranteed outcomes would be to parallelize all the track reconstruction computation across buckets. And even in the worst case scenario that we discussed initially, this would offer a fast reconstruction time over the nominal case. So that's good. The second step would be to use neural nets to learn the metric across the detector. And this will greatly improve the purity of the bucket. And even after this, we could combine this neural net method with something like the scratch code to speed up the process of making queries. And this would also mitigate the creation of duplicate tracks, which while also retaining the physics performance of NOI. So, yeah. And I'd like to thank Professor Heather Gray, Louis Guillaume-Gagnon, and IRIS-HEP for this opportunity. Thank you.
Thank you, Rohith. Any questions for Rohith?
I just wanted to say that was really nice and some pretty impressive work.
Yep.
Any other questions or comments? No? Well, thank you to all of our fellows for the talks today, and thank you to mentors, and thank you all for coming.